Imagine a robot that does not fight the world with metal, but melts into it like a living creature. It can slip through cracks, wrap around objects, and move where rigid machines simply stop. And the strange part is that nature solved this problem millions of years ago with an animal that has no bones at all. The octopus is not just intelligent, it is a master of impossible spaces. Now, engineers are copying that exact talent to build robots that can go inside the human body, under the ocean, and deep inside damaged machines. These are soft robots, flexible machines made not to resist deformation, but to use IT. They look fragile at first glance, almost toy-like, until you realize they may become the safest robots ever built for the most dangerous places on Earth. And once you understand how they work, rigid robots start to feel like the older technology. For decades, robotics was built around one assumption: strength comes from hardness. Steel frames, fixed joints, precise motors, everything designed to hold shape and never yield. That design is brilliant in factories where the world is controlled, measured, and predictable. But the real world is not a factory. Inside the body, inside pipelines, under wreckage, and at the bottom of the sea, hard robots meet environments that bend, collapse, swell, and fight back. In those places, precision alone is not enough. You need compliance, softness, adaptability, and the ability to survive contact instead of avoiding it. That single shift in thinking changed robotics forever. When engineers searched for a machine that could move through complexity, they found a creature that seems almost unreal. The octopus has no rigid skeleton, yet it can crawl, grab, twist, camouflage, and escape through openings barely larger than its eye. Its body is a living lesson in distributed control, where intelligence is not locked in one hard frame. That idea was irresistible to roboticists. In 2016, researchers at Harvard and the Wyss Institute revealed the Octobot, one of the first autonomous robots made entirely from soft materials. It had no rigid electronics inside its body, and it moved using microfluidic logic and gas generated from onboard fuel. That mattered because soft robotics had always hit the same wall: the body could be soft, but the power and control were usually hard. The Octobot did not solve everything, but it proved a radical point. A robot could think, route flow, and move without looking like a machine from the industrial age. And from that moment, the race was no longer about making robots harder, but making them smarter through softness. Soft robots work by replacing rigid joints with deformable bodies that change shape under pressure, tension, heat, magnetism, or electricity. The most common versions use air or fluid pumped into internal chambers. When one chamber expands more than another, the body bends, twists, curls, or grips. It sounds simple, but the geometry is everything. Change the thickness, the fiber angle, the material stiffness, or the chamber layout, and you change the entire behavior of the robot. In other words, the body itself becomes part of the programming. This is why soft robotics often feels closer to biology than to classic mechanics. Engineers call some of these systems artificial muscles because they contract, expand, and generate motion without traditional motors. Newer designs even combine sensing directly into the soft body, allowing the robot to feel its own shape as it moves. That is a major breakthrough because soft machines are hard to model, hard to control, and often too flexible for old robotic math. So researchers are giving them not just soft bodies, but soft perception. Some robots now integrate electronics, some use fluidic logic, and some use structural design so clever that control is partially built into the material itself. The result is a machine that does not simply move through space. It negotiates with space. This is where soft robotics stops being a lab curiosity and becomes a serious tool. In medicine, softness is not a luxury, it is a form of safety. A rigid instrument can injure tissue when the environment shifts unexpectedly. A soft one can adapt its shape, spread force, and reduce the risk of damage in minimally invasive procedures. That makes soft robotics especially promising for next-generation surgical tools, wearable devices, and internal navigation systems. Underwater, the same softness becomes a different kind of advantage. Marine environments are cluttered, fragile, and unpredictable, exactly the kind of world where hard machines can fail or break what they touch. Soft, robotic greepers inspired by octopus arms can grasp irregular objects, retrieve samples, and operate in confined underwater spaces with far more delicacy. Researchers have even built electronics-integrated soft arms that can sense and interact in broad underwater environments. And then there is industry where the most expensive problems are often hidden in the tightest spaces. Pipelines, engines, reactors, and bridge cavities are full of places humans cannot reach and rigid robots cannot navigate safely. Soft inspection robots are being designed to crawl, squeeze, and sense their way through those environments without getting stuck or causing extra damage. In disaster response, that same ability could become life-saving. After earthquakes or explosions, survivors are often separated from rescuers by spaces too small and unstable for conventional machines. A soft robot inspired by an octopus or worm could probe those voids, carry sensors, map safe paths, and reach where no rigid crawler can go. The deeper you look, the more softness starts to feel less like a compromise and more like a superpower. One of the most astonishing signs of progress came from the deepest ocean on Earth. In 2021, researchers reported a self-powered soft robot inspired by deep-sea life that operated in the Mariana Trench, without a rigid pressure vessel. That matters because the deep sea destroys ordinary engineering with crushing force. Softness, when designed correctly, can distribute stress instead of concentrating it. That flips one of engineering's oldest instincts on its head. Another breakthrough is scale, because soft robots are no longer only giant tentacle-like prototypes on lab tables. Researchers are building millimeter-scale systems with integrated sensing and motion, pushing softness toward tiny autonomous machines. The field is expanding into directions at once toward larger missions and smaller bodies, and that is usually the sign of a technology about to grow up. But this story is not all breakthrough and no friction. Soft robots are often slower than rigid robots, less precise and much harder to control mathematically. When a machine can bend almost anywhere, predicting exactly what it will do becomes a serious challenge. Materials can fatigue, puncture, leak, or drift in performance over time. Power is still a problem because many soft systems remain tethered to pumps, tubes, or external hardware. Autonomy is improving, but the dream of a fully soft, highly capable, untethered robot is still a frontier, not a finished product. And there is one more uncomfortable truth. In many applications, the future may belong not to purely soft robots, but to hybrid machines that combine softness where it helps and rigidity where it still wins. Even with those limits, soft robotics may change how humanity designs machines for contact with the unknown. We are entering an era where the most valuable environments are not open factory floors, but complex, fragile, high-risk spaces. The machines that thrive there will not be the hardest. They will be the most adaptable. That idea affects healthcare, infrastructure, ocean science, defense, manufacturing, and rescue operations all at once. It also changes our definition of what a robot is supposed to be. For generations, we imagined robots as hard, sharp, loud, and separate from life. Soft robotics suggests the opposite future, machines that borrow intelligence not just from computers, but from bodies. So go back to the image from the beginning, a robot slipping through a space that once looked impossible. That is not just a new machine. It is a new engineering philosophy, one that stops forcing the world to fit the robot and starts building robots that fit the world. And once that idea spreads, the next revolution in robotics may not arrive with a clang of metal, but with a silent squeeze into places we never thought a machine could go.